Okay. Looks like it's 5:57. 5:57. 8:44. So we'll try to get a little bit more progress done on the shared library stuff tonight, but even if I don't finish the shared library stuff, I think I'm pretty happy with today. It's not 100 pages. It's a bit slower than what I need to finish this by Thursday, but I do have a little bit of wiggle room. Not much, but we'll see how much I can get done tonight. Let's put a couple more hours into this. I'll try to stay focused and not get diverted by too much experimentation. But also, if something like this experiment that I did here with this lib test thing, I'm happy I did that because it allowed me to understand how LD preload works. And, using the same binary and the same library, just using LD preload for that library allowed me to change the behavior of the program completely, which is pretty cool if you ask me. And I've seen that done before on in other contexts, but I've never done it myself. And I eventually want to. The reason why I really wanted to experiment with this is I eventually want to write my own memory allocator. Given that I now have a little bit more understanding how memory allocation works, I have a little bit more confidence to read the glibc and maybe jemalloc libraries to get an idea for like how things are implemented. We're going to be covering memory mapping in the next couple days, so I'll have more experience with like memory mapping APIs. And just in general, it doesn't feel like that hard of a thing to implement now. Like just a malloc and a free type memory allocator. So what would be cool is if I could get like the shell running with my memory allocator instead of libc's, because the shell is going to be doing a lot of allocation and freeing and stuff. And it'd be pretty cool if I could get that running with my allocator using LD preload. So something that's been bouncing around my head, and that's the reason why I wanted to do the experiment. All right, shared library versions and naming conventions. Let's consider what is entailed by sharing library versions, shared library versioning. Typically, successive versions of a shared library are compatible with one another. Typically, successive versions of a shared library are compatible with one another, meaning that the functions in each module present the same calling interface and are semantically equivalent, i.e. they achieve identical results. Such differing but compatible versions are referred to as minor versions of a shared library. Occasionally, however, it is necessary to create a new major version of a library, one that is incompatible with the previous version. In section 41.8, we'll see more precisely what may cause such incompatibilities. At the same time, it must still be possible to continue running programs that require the older version of the library. To deal with these versioning requirements, a standard naming convention is employed for shared library real names and SO names. Real names, SO names, and linker names. Each incompatible version of a shared library is distinguished by a unique major version identifier, which forms part of the real name. By convention, the major version identifier takes the form of a number that is sequentially incremented with each incompatible release of the library. In addition to the major version identifier, the real name also includes a minor version number, which distinguishes compatible minor versions of the library within the library major version. The real name employs a format convention libname.so major ID minor ID. And there might be patches as well. Like the major version, the minor version identifier may be any string, but by convention it's either a number or two numbers separated by a dot, with the first number identifying the minor version, a second number identifying a patch level or revision number within the minor version. Some examples of real names of shared libraries are as follows. So it's kind of like Semver. The so name of the shared library includes the same major version identifier as its corresponding real name library, but excludes a minor version number. Thus, the so name has the form libname so major ID. So there's the real name, the SO name. SO name say I want this library at this major version, and then the real name is symlinked to that somehow. Usually the so name is created as a relative. So if I do like LDD on bin bash, so these are the so names, I think. Yeah, because they have the major version in them. What's weird is this so name has the full freaking path. It's a bit unusual. But yeah, basically the major version, and then the actual thing that's linked to here, and then this is probably like if we look at libc, this is probably a link. No, that doesn't look like a link. I wonder if any of these are links. That one is. So read link. Okay. Usually the synonym is created as a relative symbolic link in the directory that contains the real name. The following are the examples of pseudonyms along with the real names to which they might be symbolically linked. We got libdemo, yep, symlinks. For a particular major version of a shared library, there may be several library files distinguished by different minor version numbers. Normally, name corresponding to each major library points to the most recent minor version within the major version, as shown in the above examples for libdemo.so. This setup allows for correct version semantics during the runtime operation of shared libraries because the static linking phase embeds a copy of the minor version independent. Because the static linking phase embeds a copy of the minor version independent so name in the executable, and the so name symbolic link may subsequently be modified to point to a newer minor version of the shared library. It's possible to ensure that an executable loads the most up-to-date version of minor version of the library at runtime. Furthermore, since different major versions of a library have different so names, they can happily coexist and be accessed by the programs that require them. In addition to the real name and so name, the third name is usually defined for each shared library, the linker name, which is used when linking an executable against a shared library. Linker name is a symbolic link containing just the library name without the major or minor version numbers, and thus has the form libname.so. The linker name allows us to construct version independent link commands that automatically operate with the correct, most up-to-date version of the shared library. Cool. Typically, did I not select that? There we go. Typically, the linker name is created in the same directory as the file to which it refers. It can be linked either to the real name or to the so name of the most recent major version of the library. Usually a link to the so name is preferable, so it changes the so name are automatically reflected in the linker name. Okay. In section 41.7, we'll see that the LD config program automates the task of keeping so names up to date. LD config. And thus implicitly maintains linker names if we use the convention just described. If we want to link a program against an older major version of a shared library, we can't use the linker name. Instead, as part of the link command, we would need to indicate the required major version by specifying a particular real name or so name. The following are some examples of linker names. Table 41.1 summarizes information about the shared library real name, so name, and linker name. And figure 41.3 portrays the relationship between these names. So you got the real name, which is the name of the thing on disk. It has major and minor and possibly even patch. File holding library code, one instance per major minor version of the library. Then you got so name, one instance per major version of the library. Embedded in executable at link time, used at runtime to find library via symbolic link with same name that points to corresponding most up-to-date real name. And then finally, the linker name, symbolic link to latest name, or more usually latest so name, single instance, allows construction of version-independent link commands. Creating a shared library using standard conventions. Putting all the above information together, we now show how to build our demonstration library following the standard conventions. First, we create the object files. Then we create the shared library with the real name and the so name. Next, we create appropriate symbolic links for the so name and linker name. We can now employ ls to verify the setup, with awk used to select fields of interest. Then we can build our executable using linker name. Note that the link command makes no mention of version numbers and run the program as usual. Installing shared libraries. In the examples up to now, we create a shared library in a private use a private directory, and then use the LD library path environment variable to ensure that the dynamic linker search that directory. Both privileged and unprivileged users may use this technique. However, this technique should not be employed in production applications. More usually, a shared library is an associated symbolic, and its associated symbolic links are installed in one or more of a standard library directories, in particular one of the following: user lib directory, in which most standard libraries installed; lib directory, in which library is required during system startup should be installed, since during system startup user lib may not be mounted yet; user local lib, a directory into which non-standard or experimental libraries should be installed. Placing libraries in this directory is also useful if user lib is a network mounted share among multiple systems and we want to install a library just for use in one of the systems, or one of the directories listed in etc ld so conf. Okay, let's cut that out. I haven't encountered that before. etc ld.so conf. One's hold conf.d. So that's an include on those conf files. Let's see if there's anything under user lib ld.so conf. Fake root. Oh, weird. What is that? Give me 1 second. I want to check it out. I don't know if it's safe. What the hell is this fake root thing? Why did I run fake root? Run a command in environment faking root privileges for file manipulation. Oh, okay. Strange. Alright, installing shared libraries. We're talking about that. In most cases, copying a file into one of these directories requires super user privilege. After installation, symbolic links for so name and linker names must be created, usually as relative symbolic links in the same directory as a library file. Thus, to install our demonstration library and user lib, whose permissions only allow updates by root, we do the following. Switch to root, we move our real file into user lib. We go in there and then we create our symbolic links to it. The last two lines in the shell session create the so name and linker name symbolic links. LDconfig. The LDconfig program addresses two potential problems with shared libraries. Shared libraries can reside in a variety of directories. If the dynamic linker needs to search all these directories in order to find a library, then loading libraries can be very slow. As new versions of libraries are installed or old versions are removed, the so named symbolic links may become out of date. The LDconfig program solves these problems by performing two tasks. It searches a standard set of directories and creates or updates a cache file, the etc ld.so cache. I did see that. etc ld.so.cache. Interesting. Cache to contain the list of the latest minor versions of each of the major library versions in all of these directories. The dynamic linker in turn uses this cache file when resolving library names at runtime. To build the cache, LDconfig searches the directories specified in the file etc ld.so.conf and then lib and user lib. The etc ld.so.conf file consists of a list of directories. Path names, these should be specified in absolute path names, separated by new lines, spaces, tabs, commas, colons. In some distributions, the mandatory user local lib is included in the list. If not, you may need to add it manually. The command ldconfig-p displays the current contents of the cache. Okay. ldconfig-p. So this is like all the library files and where they're located at. So it's like a single O of 1 lookup instead of searching everything. So if I do like grep libc, and I gotta do 2 and 1. Oh no, it all has libc. Let's do something a little bit easier. Maybe like lib c++. CPP. There we go. Okay. It examines the latest minor version, i.e. the version with the highest minor number of each of the versions, each of the major version. Sorry. Of each major version of each library to find the embedded so name and then creates or updates relative symbolic links for each so name in the same directory. In order to correctly perform these actions, ldconfig expects libraries to be named according to the conventions described earlier, i.e. library real names include major and minor identifiers that increase appropriately from one library version to the next. By default, ldconfig performs both of the above actions. Command line options can be used to selectively inhibit either action. The -n option prevents rebuilding of the cache. The -x option inhibits the creation of some of the symbolic links. In addition, the -v verbose option causes ldconfig to display the outputs describing its actions. We should run ldconfig whenever a new library is installed, an existing library is updated or removed, or the list of directories in etc/ldconf is changed. An example of the operation of ldconfig: suppose we want to install two different major versions of a library. We would do this as follows. So we move the libdemo into user lib, and then we do ldconfig-v. Above, we filter out the output of ldconfig so that we see just the information related to libraries named libdemo. Next, we list the files named libdemo and user lib to verify the setup of the symbolic names. Looks Gucci. We must still create a symbolic link for the linker name as shown in the next command. Oh, it doesn't do the linker one. However, we install a new 2x minor version of our library, then since the linker name points to the latest so name, ldconfig has the effect of also keeping the linker name up to date, as the following example. I don't see it in there. Only because if we install a new minor version, yeah, that makes sense. Okay, if we are building and using a private library, i.e. one that's not installed in one of our standard directories, we can have ldconfig create the so name symbolic link for us using the -n option. This specifies that ldconfig should process only libraries in the directory on the command line and should not update the cache file. The following example, we use ldconfig to process libraries in the current working directory. So we do -n, which will prevent rebuilding of the cache. Although he did lowercase n there, and previously said it was uppercase n. Okay. Above example, we specified the full path name when running ldconfig because we were using an unprivileged account whose path environment variable did not include the sbin directory. Okay. Compatible versus incompatible libraries. Over time, we may need to make changes to the code of a shared library. Such changes result in a new version of the library that is either compatible with the previous version, meaning that we need to change only the minor version identifier of the library's real name, or incompatible, meaning we must define a new major version of the library. A change to a library is compatible with an existing library version if all of the following conditions hold true. The semantics of each public function and variable in the library remain unchanged. In other words, each function keeps the same argument lists and continues to produce its specified effect on global variables and returned arguments, and returns the same result value. Thus, changes that result in an improvement in performance or fix a bug resulting in closer conformance to specified behavior can be regarded as compatible changes. No function or variable in the library's public API is removed. It is, however, compatible to add new functions and variables to the public API. Structures associated within and returned by each function remain unchanged. Similarly, public structures exported by the library remain unchanged. One exception to this rule is that under certain circumstances, new items may be added to the end of an existing structure, though even this may be subject to pitfalls if, for example, the calling program tries to allocate an array of this structure type. Library designers sometimes circumvent this limitation by defining exported structures to be larger than is required in the initial release of the library, with some extra padding fields being reserved for future use. If none of these conditions is violated, then the new library name can be updated by adjusting the minor version of the existing name. Otherwise, a new major version of the library should be created. Upgrading shared libraries. One of the advantages of shared libraries is that a new major or minor version of a library can be installed even while running programs are using an existing version. All we need to do is create the new library version, install it in the appropriate directory, and update the so name and linker name symbolic links as required, or more usually have ldconfig do the job for us. To produce a new minor version, a compatible upgrade of the shared library, we would do the following. Makes sense. Assuming the linker name was already correctly set up, we would not need to modify it. Already running programs will continue to use the previous minor version of the shared library. Only when they are terminated and restart will they too use the new minor version of the shared library. If we subsequently wanted to create a new major version of the shared library, we would do the following. As can be seen in the above output, ldconfig automatically creates the so name symbolic link for the new major version. However, as the last command shows, we must manually update the linker name symbolic link, specifying library search directories in an object file. We have already seen two ways of informing the dynamic linker of the location of shared libraries using the LD library path environment variable and installing a shared library into one of the standard library directories, lib, user lib, or one of the directories listed etc ld soconf. There is a third way. During the static editing phase, we can insert into the executable a list of directories that should be searched at runtime for shared libraries. If this is useful if we have libraries that reside in fixed locations that are not among the standard locations searched by the dynamic linker. To do this, we employ the rpath linker option when creating the executable. So we say gccg wall wl rpath. And then we give it the rpath. The above command copies the string home make dir mtk pdir into the runtime library path list of the executable prog, so that when the program runs, the dynamic linker will also search this directory when resolving shared library references. If necessary, the rpath option can be specified multiple times. All of the directories are concatenated into a single ordered rpath list placed in the executable file. Alternatively, multiple directories can be specified as a colon-separated list within a single rpath option. At runtime, the dynamic linker searches the directories in the order they were specified in the rpath options. An alternative to the rpath option is the ld runpath environment variable. This variable can be assigned a string containing a series of colon-separated directories that are used as the rpath list when building an executable file. ld runpath is employed only if the -rpath option is not specified when building the executable. Using the -rpath linker option when building a shared library. The -rpath linker option can also be useful when building a shared library. Suppose we have one shared library libx.so that depends on number libx2.so, as shown in figure 41.4. So we got a program, it's called x1, and it's linking dynamically against libx1.so, and then it's saying, hey, you gotta pull in x2, which is d2 libx2.so. Suppose also that these libraries reside in non-standard directories d1 and d2 respectively. We now go through the steps required to build these libraries and the program that uses them. First, we build libx2.so in the directory pdir d2. Okay. Next, we build, since libx.so depends on libx2, which is not in the standard directory, we specify the latter's runtime location with the rpath linker option. This can be different from the link time location of the library specified by the L option, although in this case the two locations are the same. So you say, hey, give it rpath d2, finally, we build the main program in the pdir directory, since the main program makes use of libx1.so, and this library resides in a non-standard directory. We again employ rpath linker option. Note that we did not need to mention libx2.so when linking the main program, since the linker is capable of analyzing the rpath list in libx1.so. It can find libx2.so and thus is able to satisfy the requirement that all symbols can be resolved at static link time. We can use the following commands to examine prog and libx1.so in order to see the contents of the rpath lists. We can also view the rpath list by grepping the output of the readelf dynamic, or equivalently readelf-d command. We can use the LDD command to show the complete set of dynamic dependencies of prog. The elf, dt, rpath, and dt runpath entries. The original elf specification, only one type of rpath list could be embedded in an executable or shared library. This corresponded to the dt rpath tag in an elf file. Later elf specifications deprecated dt rpath and introduced a new tag, dt runpath, for representing rpath lists. The difference between these two types of rpath lists is their relative precedence with respect to the LD library path environment variable when the dynamic linker searches for shared libraries at runtime. DT rpath has higher precedence, while DT runpath has lower precedence. By default, the linker creates the rpath list as a DT rpath tag. To have the linker instead create the rpath as a DT runpath entry, we must additionally employ enable new dtags linker option. If we rebuild our program using this option, inspect the resulting executable file with odds jump, we see the following. It can be seen the executable contains both R path and a run path tags. The linker duplicates the R path list entry in this way for the benefit of the old dynamic linkers that may not understand the DT run path. Dynamic linkers that understand the DT run path tag ignore the DT R path tag. Oh, okay. Using origin in R path. Suppose that we want to distribute an application that uses some of its own shared libraries, but we don't want to require the user to install the libraries in one of the standard directories. Instead, we would like to allow the user to unpack the application under an arbitrary directory of their choice and then immediately be able to run the application. The problem is that the application has no way of determining where its shared libraries are located unless it requests the user to set the LD library path or require the user to run some sort of installation script that identifies the required directories. Neither of these approaches is desirable. To get around this problem, the dynamic linker is built to understand a special string origin in an RPath specification. Dynamic linker interprets the string to mean the directory containing the application. This means that we can, for example, build an application with the following command. This presumes that at runtime the application shared libraries will reside in the subdirectory lib under the directory that contains the application executable. We can provide the user with a simple installation package that contains the application and associated libraries, and the user can install the package in any location and then run the application, i.e. so-called turnkey application. Finding shared libraries at runtime. When resolving library dependencies, the dynamic linker first inspects each dependency to see if it is contains a slash. Yeah, because some of these contain slashes. Which can occur if we specify an explicit library path name when linking the executable. If a slash is found, then the dependency string is interpreted as a path name, either absolute or relative, and the library is loaded using that path name. Otherwise, the dynamic linker searches for the shared library using the following rules. If the executable has any directories listed in its DT run path, RPath runtime library path, and the executable does not contain a run path list, then these directories are searched. If the executable is a set user ID or set group ID program, then the LD path is ignored. It's a security measure to prevent users from tricking the dynamic linker into loading a private version of a library with the same name as the library required by an executable. That's a good idea. If the executable has any directories listed in its DT run path, runtime library path list, then these directories are searched in order that they were supplied in linking the program. The file etc LDSO cache is checked to see if it contains an entry for the library. Directories at lib and user lib are searched in that order. Runtime symbol resolution. Suppose that a global symbol, i.e. a function or variable, is defined in multiple locations, such as in an executable and in a shared library, or in multiple shared libraries. How is a reference to that symbol resolved? For example, suppose we have a main program in a shared library, main program and a shared library, both of which define a global function XYZ. Another function within a shared library that calls XYZ as shown in figure 41.5. when we build the shared library and execute the program and then run the program, this is what we see. Yeah, I mean, the main's going to call its main calls func calls xyz in the program. From the last line of output, you can see the definition of xyz, and the main program overrides and interposes the one in the shared library. This may at first appear surprising. There's good historical reason why things are done this way. The first shared library implementations were designed so that the default semantics for simple resolution exactly mirrored those of applications linked against static equivalents of the same libraries. This means that the following semantics apply. A definition of a global symbol in the main program overrides the definition in the library. If a global symbol is defined in multiple libraries, then a reference to that symbol is bound to the first definition found by scanning libraries in the left to right order in which they were listed on the static link command line. Although these semantics make the transition from static to shared libraries relatively straightforward, they can cause some problems. The most significant problem is that these semantics conflict with the model of a shared library as implementing a self-contained subsystem. By default, a shared library can't guarantee that a reference to one of its own global symbols will actually be bound to the library's definition of that symbol. Consequently, the properties of a shared library can change when it is aggregated into a larger unit. This can lead to applications breaking in unexpected ways and also makes it difficult to perform divide and conquer debugging. In the above scenario, if we wanted to ensure that the invocation of XYZ in the shared library actually called the version of the function defined within the library, then we could use the be symbolic linker option when building the shared library. So the difference here is just when we do the shared library, say be symbolic, and then the rest of it's the same. And now we get foo XYZ. The be symbolic linker option specifies that references to global symbols within a shared library should be preferentially bound to definitions if they exist within that library. Note that regardless of this option, calling XYZ from the main program would always invoke the version of XYZ defined in the main program, using a static library instead of a shared library. Although it is almost always preferable to use shared libraries, there are occasionally situations where static libraries may be appropriate. In particular, the fact that a statically linked application contains all of the code that it requires at runtime can be advantageous. For example, statically linking is useful if the user can't or doesn't wish to install a shared library on the system where the program is to be used, or if the program is to be run on an environment, perhaps a root jail, for example, or a container, where shared libraries are unavailable. In addition, even a compatible shared library upgrade may unintentionally introduce a bug that breaks an application. By linking an application statically, we can ensure that it is immune to changes in the shared libraries on the system, and that it has all the code it requires to run at the expense of a larger program size, consequent increased disk and memory requirements. By default, where the linker has a choice of a shared and a static library of the same name, e.g. when using link sumdir links demo, and both libdemo and libdemo.a exist, the shared version of the library is used. To force usage of static versions of the library, we may do one of the following. Oops, sorry, I'm on the wrong page here. My bad. I actually was quite far behind. I'm getting tired, sorry. Specify the path name of the static library, including the .a extension on the GCC command line. Specify the static option in GCC. Use the GCC option WLB static and WLB dynamic to explicitly toggle the linker's choice between static and shared libraries. These options can be intermingled with .l options on the GCC command line. The linker processes the options in the order in which they are specified. Summary. An object library is an aggregation of compiled object modules that can be employed by programs that are linked against the library. Like other Unix implementations, Linux provides two types of object libraries: static libraries, which are the only type of library available under early Unix systems, and a more modern shared libraries. Because they provide several advantages over static libraries, shared libraries are the predominant type of library in use on contemporary Unix systems. The advantages of shared libraries spring primarily from the fact that when a program is linked against the library, copies of the object modules required by the program are not included in the resulting executable. Instead, the static linker merely includes information in the executable file about the shared libraries that are required at runtime. When the file is executed, the dynamic linker uses information to load the required shared libraries. At runtime, all programs using the same shared libraries share a single copy of that library memory. Since shared libraries are not copied into executable files, and a single memory resident copy of the shared library is employed by all programs at runtime, shared libraries reduce the amount of disk space and memory required by the system. It's not that big of a deal, though. The shared library name provides a level of indirection in resolving shared library references at runtime. Says this name that could be part of the shared library. If a shared library has a name, then this name, rather than the library's real name, is recorded in the resulting executable produced by the static linker. A version scheme whereby a shared library is given a real name of the form libname.so major minor id, while the name has a form libname.so major ID, allows for the creation of programs that automatically employ the latest minor version of the shared library without requiring the programs to be relinked, while also allowing for the creation of new incompatible major versions of the library. In order to find a shared library at runtime, the dynamic linker follows a standard set of search rules, which include searching a set of directories, e.g. lib and user lib, in which most standard libraries are installed. Good lord, that's a lot of information. We got another chapter or two. Further information. So it is 6:45. Various information related to static and shared libraries can be found in the AR, archive, GCC, LD, the linker, LD config, LD.so, dlopen, readelf. We didn't cover dlopen. In object dump manual pages, and in the info documented for LD. Covers many of the finer details of writing shared libraries on Linux. Further useful information can also be found in David Wheeler's program Library How To, which is online at the LDP website. The GNU shared library scheme has many similarities to that implemented in Solaris, and therefore it is worth reading Sun's Linker and Libraries Guide. For further information and examples, provide an introduction to the operation of static and dynamic linkers. Sun.com isn't even a thing anymore. It goes to Oracle. Information about GNU libtool, a tool that shields programs from the implementation specific details of building shared libraries, can be found online at so-and-so. The document executable and linking format from the Tools Interface Standard Committee provides details on ELF, executable linking format. This document can be found online. Also provides a lot of useful detail on ELF. good on the exercises. Okay, so we are on page 859. 859. And it is 6:47. Okay. We might get pretty close. Depends on how much time I spend on this next chapter. 2, 3, 4. Alrighty. Chapter 42. Let's, I'm gonna write this. I'm gonna also vim up readme, and I thought we already had this. Get log 1, 38, 39, 40. Get show at stat, 38, 39, 40. Oh, I didn't mark them. Bummer. Let's write that out. Okay. It will kill us. So that was supposed to take us up to 40. So let's vim the readme. Go over to here. Forgot to mark these things as X. When you get status, get add readme, get status, get CI, amend, no edit. And now when we get show, it says 38, 39, 40, and those are checked now. Great. So now we have 41. We'll add 42 here, which is advanced features of shared libraries. Oops. Advanced features of shared libraries. Mark an X on that. And then readme and chapter 41. Okay. Get ignore, build, clean, lib test, run. Okay. And then we'll say get DC. And everything looks good to me. Cool, cool, cool. Get CI. Now we can say, or let's do another get DC, just make sure the readme is correct. Yeah. Get CI, and we'll say finish chapter 41. Cool. Okay, so now that we're clean, we can start reading. Let's see here. The previous chapter covered the fundamentals of shared libraries. This chapter describes a number of advanced features of shared libraries, including the following. Dynamically loading shared libraries. That's cool. That's the DL open stuff. You basically open up the shared object, and then you look up the symbols, and then you call you cast a symbol. When you look up the symbol, it gives you back a void star. You cast it into the function pointer, and then you call it. I've done that before in Go plugin stuff. All right. Controlling the visibility of symbols defined by a shared library. Controlling the visibility of symbols defined by a shared library. I think that's the extern, right? What do they mean by visibility too? Does that just mean that there is one or there isn't one? Using linker scripts to create version symbols. That's what I've seen in a lot of these things, are the version symbols. Using initialization and finalization functions to automatically execute code when a library is loaded and unloaded. um, shared library preloading, and using LD debug to monitor the operation of the dynamic linker. Cool. I mean, this is some stuff that some of this stuff I've done before. So we're getting into some things though that I haven't done, like LD debug I've never used before. Dynamically loaded libraries. When an executable starts, the dynamic linker loads all of the shared libraries in the program's dynamic dependency list. Sometimes, however, it can be useful to load libraries at a later time. For example, a plugin is loaded only when it is needed. This functionality is provided by an API to the dynamic linker. This API, usually referred to as the DLOpen API, originated on Solaris, and much of it is now specified in SUSV3. The DLOpen API enables a program to open a shared library at runtime, search for a function by name in that library, and then call the function. A shared library loaded at runtime in this way is commonly referred to as a dynamically loaded library, or plugin, and is created in the same way as any other shared library. The core DLOpen API consists of the following functions, all of which are specified in SUSV3. DLOpen function opens a shared library, returning a handle used by subsequent calls. DLSym function searches a library for a symbol, a string containing the name of a function or variable, and returns its address. DLClose function closes a library previously opened by DLOpen. DLError function returns an error message string and is useful after a failure returned from one of the preceding functions. The glibc implementation also includes a number of related functions, some of which we describe below. To build programs that use the DLOpen API on Linux, we must specify the LDL option in order to link against the libdl library. I just think it's funny that's called LDL. Opening a shared library, DLOpen. I've done this a dozen times before. The DLOpen function loads the shared library named in libfilename into the calling process virtual address space and increments the count of open references to the library. If libfilename contains a slash, DLOpen interprets it as an absolute or relative path name. Otherwise, the dynamic linker searches for the shared library using the rules described in section 4111. On success, DLOpen returns a handle that can be used to refer to the library and subsequent calls to functions in the DLOpen API. If an error occurred, e.g. the library couldn't be found, DLOpen returns null. If the shared library is specified by libfilename contains dependencies on other shared libraries, DLOpen also automatically loads those libraries. This procedure occurs recursively if necessary. We refer to this set of such loaded libraries as this library's dependency tree. It is possible to call DLOpen multiple times on the same library file. The library is loaded into memory only once by the initial call, and all calls return the same handled value. However, the DLOpen API maintains a reference count for each library handle. If this count is incremented by each call to DLOpen and decremented by each call to DLClose. Only when the count reaches 0 does DLClose unload the library from memory. The flags argument is a bit mask that must include exactly one of the constants, RTLD lazy and RTLD now, with the following meanings. I didn't see the flags. Oh, there it is. Lazy, undefined function symbols in the library should be resolved only as the code is executed. If a piece of code requiring a particular symbol is not executed, that symbol is never resolved. Lazy resolution is performed only for function references. References to variables are always resolved immediately. Specifying lazy flag provides behavior that corresponds to the normal operation of the dynamic linker when loading the shared library libraries identified in the executable's dynamic dependency list. RTLD now, all undefined symbols in the library should be immediately resolved before deal open completes, regardless of whether they will be required. As a consequence, opening the library is slower, but any potential undefined function symbol errors are detected immediately instead of at some later time. This can be useful when debugging an application or simply to ensure that an application fails immediately on an unresolved symbol rather than doing so after executing it for a long time. By setting the environment variable LD by now to a non-empty string, we can force the dynamic linker to immediately resolve all symbols when loading the shared libraries identified in the executable's dependency list. This environment variable is effective in glibc 211 and later. Setting LD by now overrides the effect of the deal open RTLD lazy flag. It is also possible to include further flag values in flags. The following flags are specified in susv3. RTLD global. Ugh. How many more flags does this thing have to go through? God, a whole page and a half. Okay. Alright, global. Symbols in this library and its dependency tree are made available for resolving references in other libraries loaded by this process and also for lookups via DLSym. Local. This is the converse of global, and the default if neither constant is specified. Specifies that symbols in this library and its dependency tree are not available to resolve references in subsequent loaded libraries. Susv3 doesn't specify default if neither global nor local is specified. Most Unix implementations assume the same default local as Linux, but if you assume default global, Linux also supports a number of flags that are not specified in susv3. RTLD no delete, don't unload the library during a DL close. Even if the reference count falls to 0, this means that the library's static variables are not reinitialized if the library is later reloaded by DL open. We can achieve a similar effect for libraries loaded automatically by the dynamic linker by specifying the gcwl-z no delete option when creating the library. RTLD no load, don't load the library. This serves two purposes. First, we can use this flag to check if a particular library is currently loaded as part of the process address space. If it is, DL open returns the library handle. If not, DL open returns null. Second, we can use this flag to promote the flags of an already loaded library. For example, we can specify no load, global, and flags when using DL open on a library previously opened with RTLD local. Deep bind, when resolving symbol references made by this library. Search for definitions in the library. When resolving symbol references made, search for definitions in the library before searching for definitions in libraries that have already been loaded. This allows a library to be self-contained using its own symbol definitions in preference to global symbols with the same name defined in other shared libraries that have already been loaded. This is similar to the effect of the B symbolic linker option described in section 41.12. The RTLD no delete and the RTLD no load flag are also implemented in the Solaris DL open API, but are available on a few other Unix implementations. The deep bind flag is Linux specific. As a special case, we can specify a lib file name as null. This causes DL open to return a handler for the main program. I remember running into this recently. susv3 refers to this as a handle for the global symbol object. Specifying this handle is something called a DLSym causes the requested symbol to be sought in the main program. followed by all shared libraries loaded at program startup, and then all libraries dynamically loaded using with the RTLD global flag. I was thinking about when I work, I think I'm going to be working on a memory allocator. And when I do that, I'm going to write some tests. And what would be really cool is if I just write my tests with like test underscore in the function name. And then the test runner will just like use DLOpen on itself on null. And then look up symbols that match with like the test underscore prefix and just run them all. I thought that, I was thinking about doing that as like a really primitive test runner. Thought that would be pretty cool to play around with. Diagnosing errors, DL error. If we receive an error returned from DLOpen or one of the other functions in the DLOpen API, we can use DL error to obtain a pointer to a string that indicates the cause of the error. DL error function returns null if no error has occurred since the last call to DL error. We'll see how this is useful in the next section. Attaining the address of a symbol .dlsim. This is all stuff I've done before, so I'm not learning anything new here. The dlsim function searches for the named symbol, a function or variable, in the library referred to by handle, and in that library's dependency tree. Boop. If symbol is found, dlsim returns its address, otherwise dlsim returns null. The handle argument is normally a library handle returned by previous call to DLOpen. Alternatively, it may be one of the so-called pseudo handles described below. A related function, DLVSim, handle symbol version, is similar to dlsim, but can be used to search a symbol version library for a symbol definition whose version matches the string specified in version. We describe symbol versioning in section 4232. The GNU source feature test macro must be defined in order to obtain the declaration of this function from dlfcn.h. The value of a symbol returned by dlsim may be null, which is indistinguishable from the symbol not found return. In order to differentiate the two possibilities, we must call DL error beforehand to make sure that any previously held error string is cleared. And then if after the call to dlsim, DL error returns a non-null value, then we know that an error occurred. If symbol is the name of a variable, then we can assign the return value of dlsim to an appropriate pointer type. And obtain the value of the variable by dereferencing the pointer. If symbol is the name of a function, then the pointer returned by dlsim can be used to call the function. We can store the value returned by dlsim in a pointer to the appropriate type, such as the following. Int func p int. However, we can't simply assign the result of dlsim to such a pointer as in the following example. The reason is that ISOC standard leaves the result of casting between function pointers and void star undefined. Solution is to use the following somewhat clumsy cast. Having used dlsim to obtain a pointer to the function, we can then call the function using the usual C syntax for dereferencing function pointers. Instead of the star void star star syntax above, one might consider using the following, seemingly equivalent code when assigning the return value of DLSim. However, for this code, GCC pedantic warns that ANSI C forbids the use of cast expression as L values. The star void star star syntax doesn't incur this warning because we are assigning to an address pointed to by the assignment's L value. On many Unix implementations, we can use casts such as the following to eliminate warnings from the C compiler. However, the specification of DLSim in SUSV3 technical corriendum number 1 notes that the ISOC standard nevertheless requires compilers to generate a warning for such a conversion and proposes the star void star star syntax above. SUSV3 TC1 noted that because of the need for the star void star star syntax, a future version of the standard may define a separate DLSim-like APIs for handling data and function pointers. However, SUSV4 contains no changes with respect to this point. Using library pseudo handles with DLSim. Instead of specifying a library handle returned by a call to DLOpen, either of the following pseudo handles may be specified as a handle argument for DLSim. Default index, default search for a symbol starting with the main program and then proceeding in order through the list of shared libraries loaded, including those libraries dynamically loaded by DLOpen. With the RTLD global flag, this corresponds to the default search mode employed by the dynamic linker. Next, search for symbol in shared libraries loaded after the one invoking DLSim. This is useful when creating a wrapper function with the same name as the function defined elsewhere. For example, in our main program, we may define our own version of malloc, which perhaps does some bookkeeping of memory allocation, and this function can invoke the real malloc by first obtaining its address via the call func DLSim RTLD and next malloc. The pseudo handle values listed above are not required by SUSV3, which nevertheless reserves them for future use and are not available on all Unix implementations. In order to get the definition of these constants from dlfcn.h, we must define the GNU source test feature test macro. Boom, boom, boom. Example program. Listing 42.1 demonstrates the use of DLOpen API. This program takes two command line arguments, the name of the shared library to load and the name of the function to execute within that library. The following example demonstrates the use of this program. So what I noticed with DLSim is that it is like an exact match type thing. It's not, oh, can you match a substring? So yeah, I might not be able to do what I intended to do. So this one we run download, we give it the dynamic link, dynamic library, and then the symbol x1, and it says, hey, I called mod x1, and then you can do the same thing. I don't know why you give it library path, get the same result. I don't understand what that's saying. And the first of the above commands, DLOpen notes that the library path includes a slash and thus interprets it as a relative. Oh, okay. Path name in this case to a library in the current working directory. The second command, we specify the library search path. This search path is interpreted according to the usual rules for dynamic linker. In this case, likewise, to find the library in the current working directory. So this is a super simple main program. We just import the dlfcn.h. We have our main. We got a bunch of variables that we declare. So we have lib handle, a handle for the shared library, which is just a void star. That's one thing I didn't like about This DL open stuff is that it uses a bunch of void stars. Just doesn't scream polished, you know. Pointer to a function with no arguments. So that is a function pointer called func p that returns nothing and receives nothing. And then we got our const char star error. Okay. And then we say if argc is not equal to 3, which means that we have 3 elements, which would match our call syntax up here. Then we print out our usage, and then we do a DL open on argv1, say lazy, and so we get our handle out. The handle is null, we handle the error. We clear DL error, then we do DL sim, and then we see if we got a DL error. The DL sim we assign into the function pointer, we get a reference to it, and then we cast that as a void star star, which makes sense, and then we dereference it. I mean, it's not an insane syntax. I mean, it's pretty crazy, but it's not too insane. If the address returned by DLSim is not non-null, try calling it as a function that takes no arguments. This says, hey, it was null. And then we call it. And then at the end we close our lib handle because we're done calling stuff. Makes sense, pretty straightforward. Closing the shared library. The DL close function closes a library. The DL close function decrements the system counter of open references to the library referred to by handle if the reference count falls to 0 and no symbols in the library are required by other libraries. Then the library is unloaded. This procedure is also recursively performed for the libraries in this library's dependency tree, and implicit DL close of all libraries is performed on process termination. From glibc onward, a function within the shared library can use at exit or on exit to establish a function that is called automatically when the library is unloaded. Attain information about loaded symbols, DL adder. Given an address in adder, typically one obtained by earlier call to DL sim, DL adder gives a structure containing information about that address. So you say, hey, here's a random address, give me some information about it. The info argument is a pointer to a caller allocated structure that has the following form. So it has the F name, the path name of the shared library, F base, the base address to which the library is loaded, S name, name of the symbol whose definition overlaps, and S adder, actual value of the symbol returned by DLY S name, returned in. Cool. The first two fields of the DL info structure specify the path name and runtime base address of the shared library. I'm starting to zone out here. It's 716. How many pages we got here? 1, 2, 3, 4, 5, 6, 7, 8, 9. We've got 9 pages left. Can we finish that? Okay, I'll get it done. Okay, the first two fields of the DL open structure specify the path name and runtime base name address of the shared library containing the address specified by adder. The last two fields return information about that address, assuming that adder points to the exact address of the symbol of the shared library. Then sadder returns the same value that was passed in adder. Sus3 doesn't specify DL adder, and this function is not available in all Unix implementations. Accessing symbols in the main program. Suppose that we use DL open to dynamically load a shared library and use DL sim to obtain the address of function X from that library, and then call X if X in turn calls a function y, then y would normally be sought in one of the shared libraries loaded by the program. Sometimes it is desirable instead to have x invoke an implementation of y in the main program. This is similar to the callback mechanism. In order to do this, we must make the global scope symbols in the main program available to the dynamic linker by linking the program using the export dynamic linker option. Equivalently, we can write the following. Using either of these options allows a dynamically loaded library to access global symbols in the main program. The GCC R dynamic option and the GCC E option are further synonyms for export dynamic. Controlling symbol visibility. A well-designed shared library should make visible only those symbols, functions, and variables that form part of its specified application binary interface. The reason for this are as follows. If a shared library designer accidentally exports unspecified interfaces, then authors of applications that use the library may choose to employ these interfaces. This creates a compatibility problem for future upgrades of the shared library. The library developer expects to be able to change or remove any interface other than those in the documented API, while the library user expects to continue using the same interfaces with the same semantics that they currently employ. During runtime symbol resolution, any symbols that are exported by a shared library might interpose definitions that are provided in other shared libraries. Exporting unnecessary symbols increases the size of the dynamic symbol table that must be loaded at runtime. All of these problems can be minimized or avoided altogether if the library designer ensures that only the symbols required by the library's specific API are exported. The following techniques can be used to control the export symbol of symbols. In a C program, we can use the static keyword to make a symbol private to a source code module, thus rendering it unavailable for binding by other object files. As well as making a symbol private in source code module, the static keyword also has a converse effect. If a symbol is marked as static, then all references to symbol in the same source file will bond to that definition of the symbol. Consequently, these references won't be subject to runtime interposition by definitions from other shared libraries in the manner described in section so-and-so. This effect of a static keyword is similar to the B symbolic linker option described in section 41.12, with the difference that the static keyword affects a single symbol within a single source file. The GNU-C compiler GCC provides a compiler-specific attribute declaration that performs a similar task to the static keyword. So you can say attribute visibility hidden. Whereas the static keyword limits the visibility of a symbol to a single source code file, the hidden attribute makes a symbol available across all source code files that compose the shared library, but prevents it from being visible outside the library. As with the static keyword, the hidden attribute also has the converse effect of preventing symbol interposition at runtime. Version scripts, section 42.3, can be used to precisely control symbol visibility and to select the version of the symbol for which the reference is bound. When dynamically loading a shared library, the DLOpen RTLD global flag can be used to specify that the symbols defined in the library should be made available for binding by subsequently loaded libraries, and the export dynamic linker option can be used to make the global symbols of the main program available to dynamically loaded libraries. For further details on this topic of symbol visibility, see Draper. Linker version scripts. So that's going to be a couple pages here. Yeah, with at, I'm curious about that. And then we got initialization finalizer, preloading shared libraries with LD preload, monitoring the dynamic linker, LD debug, and summary. Okay, not too much. All right, linker version scripts. A version script is a text file containing instructions to the linker, LD. In order to use a version script, we must specify the version script linker option. So we say, hey, WL version script, myscriptfile.map. Version scripts are commonly but not universally identified using extension .map. The following sections describe some uses of version scripts. Controlling symbol visibility with version scripts. One use of version scripts is to control the visibility of symbols that might otherwise accidentally be made global, i.e. visible to applications linking against the library. As a simple example, suppose that we are building a shared library from the three source files viscom, visf1, and visf2, which respectively define functions viscom, visf1, and visf2. The viscom function is called by visf1 and visf2, but is not intended for direct use by applications linked against the library. Suppose we build the shared library in the usual way. So we do this. We get all of our objects and we cram them into a shared library. If we use the following readelf command to list the dynamic symbols exported by the library, we see the following. All three of them visible. The shared library exported three symbols, viscom, visf1, and visf2. However, we would like to ensure that only the symbols visf1 and vis2 F2 are exported by the library. We can achieve this result by using the following version script. So then we say, hey, global visf1, visf2, local is no bueno. The identifier ver1 is an example of a version tag. As we'll see in the discussion of symbol versioning, section 42.3.2, a version script may contain multiple version nodes, each grouped with braces, and prefixed with a unique version tag. If we are using a version script only for the purpose of controlling symbol visibility, then the version tag is redundant. Nonetheless, older versions of LD require it. Modern versions of LD allow the version tag to be omitted. In this case, the version node is said to have an anonymous version tag, and no other version nodes may be present in the script. Within the version node, the global keyword begins a semicolon separated list of symbols that are made wait a minute. Here it is. Begins a semicolon separated list of symbols that are made visible outside the library. The local keyword begins a list of symbols that are to be hidden from the outside world. The asterisk here illustrates the fact that we can use wildcard patterns in these symbol specifications. The wildcard characters are the same as those used for shell file name matching. For example, star and question mark. See glob manual page for further details. In this example, using asterisks for the local specification says that everything that wasn't explicitly declared global is hidden. If we did not say this, then viscom would still be visible, since the default is to make C global symbol visible outside of shared libraries. We can then build our shared library using the version script as follows. So just when we build our shared library, we say version script is vismap. Wait a minute, we're on the wrong page here. There we go. Using readelf once more shows that viscom is no longer externally visible. Cool. Now we talk about symbol versioning for 3 pages, and then some other topics. Symbol versioning. Symbol versioning allows a single shared library to provide multiple versions of the same function. Each program uses the version of the function that was current when the program was statically linked against the shared library. As a result, we can make an incompatible change to a shared library without needing to increase the library's major version number. Carried to an extreme, symbol versioning can replace the traditional shared library major and minor versioning scheme. Symbol versioning is used in this manner in glibc 2.1 and later, so that all versions of glibc from 2.0 onward are supported within a single major library version. libc SO6. We demonstrate the use of symbol versioning within a simple example. We begin by creating the first version of a shared library using a version script. Okay. Within a version script, the hash character starts with a comma. Okay. To keep the example simple, we avoid use of explicit library so names and library major version numbers. At this stage, our version script svv1.map serves only to control the visibility of the shared library symbols. XYZ is exported, but all their symbols, of which there are none in this small example, are hidden. Next, we create a program P1 which makes use of this library. It's like, hey, I want to use that libsv. Yep. When we run this program, we see the expected result. I didn't know you could do 4 declarations in the body of a function. I didn't know you could do that. But I had to do it at the global level. Now suppose that we want to modify the definition of XYZ within our library while still ensuring that program P1 continues to use the old version of this function. To do this, we must define 2 versions of XYZ within our library. Okay. Our 2 versions of XYZ are provided by the functions XYZ_old and XYZ_new. The XYZ_old function corresponds to our original definition of XYZ, which is the one that should continue to be used by program P1. The XYZ_new function provides the definition of the XYZ to be used by programs linking against the new version of the library. The 2.symver assembler directives are the glue that ties the 2 functions to different version tags in the modified version script, shown in a moment. Which is interesting, you don't have to be forward declared, they're just assembly instructions. That we use to create the new version of the shared library. The first of these directives says that XYZ_old is the implementation of XYZ to be used by applications linked against the version tag ver1, and the XYZ_new is the implementation of XYZ used to be applications linked against the version tag vers2. Okay. The use of @ rather than @ in the second sender directory indicates that this is the default definition of XYZ to which applications should bind when statically linking against this shared library. Exactly one of the .symver directives for a symbol should be marked using @. The corresponding version script for our modified library is as follows. So now we say, okay, we got version 1 and version 2. And version 2 has an additional global PQR. This version script provides a new version tag, ver2, which depends on the tag ver1. This dependency is indicated by the following line, ver1. Version tag dependencies indicate the relationship between successive library versions. Semantically, the only effect of version tag dependencies on Linux is that a version node inherits global and local specifications from the version node upon which it depends. Dependencies can be chained so that we could have another version node tagged ver3, which depends on ver2, and so on. The version tag names have no meaning in themselves. The relationship with one another is determined only by the specified version dependencies, and we choose the names var1 and var2 merely to be suggestive of these relationships. To assist maintenance, recommended practice is to use version tags that include the package name and the version number. For example, glibc uses version tags with names such as glibc2, glibc 2.1, and so on. The var2 version tag also specifies that the new function pqr is to be exported by the library and bound to the version 2 version of tag. If we didn't declare pqr in this manner, then the local specification of var2 version tag inherited from version 1 version tag would make pqr invisible outside the library. Note also that if we omitted the local specification altogether, then the symbols xyz old and xyz new would also be exported by the library, which is typically not what we want. We now build a new version of the library in the usual way. Now we can create a new program, P2, which uses the new definition of XYZ, while program P1 uses the old version of XYZ. Doesn't it need... Huh. The version tag dependencies of an executable are recorded at static link time. We can use object-t to display the simple table of each executable, thus showing the different version tag dependencies of each program. So it like links directly to that symbol. It's not even like, yeah, it doesn't even say XYZ. It says XYZ at this version. And it does add too. Doesn't that break the that's a little sketch. We can also use readelf-s to obtain similar information. Further information about symbol versioning can be found using the command info ld scripts version and at Red Hat Drepper symbol versioning. That might actually be a good document to read at some point. people.redhat.com/drepper/symbol-versioning. Yeah, this Drepper guy, he's like prolific, and Red Hat does like really great work. Initialization and finalization functions. It is possible to define one or more functions that are executed automatically when a shared library is loaded and unloaded. This allows us to perform initialization and finalization actions when working with shared libraries. Initialization and finalization functions are executed regardless of whether the library is loaded automatically or loaded explicitly using the DL open interface. Initialization and finalization functions are defined using the GCC constructor and destructor attributes. Each function that is to be executed when the library is loaded should be defined as follows. Constructor some name load void. Unload function should be similarly defined. Some name unload. Function names some name load and some name unload can be replaced by any desired names. It is also possible to use the GCC constructor and destructor attributes to create initialization and finalization functions in a main program. The _init and _fini functions. An older technique for shared library initialization and finalization is to create two functions, init and fini, as part of the library. The void init void function contains code that is to be executed when the library is first loaded by the process. The void fini function contains code that is to be executed when the library is unloaded. If we create init and fini functions, then we must specify GCC no start file options when building the shared libraries in order to prevent the linker from including default versions of these functions. Using the WL init and WL fini linker options, we can choose alternative names for these two functions if desired. Use the init and fini is now considered obsolete in favor of GCC constructor and destructor for attributes, which among other advantages allows us to define multiple initialization and finalization functions. Cool. Preloading shared libraries. This is what I was. Oh, hey, buddy. I'm studying. Yeah, sorry, I'm like really bad at reading chat when I'm reading. I'm reading the Linux Programming Interface book, and it is a long one. I'm at page 873 out of 1,400 pages. Sorry if I miss your chat. I just like zone out sometimes. You're interested, yeah. No Discord, unfortunately. What do I do for a living? I'm like kind of retired at this point in my life. So I just mess around on the internet all day, learning cool stuff about computers and hanging out, enjoying life. I just started streaming at the start of the year here with this project in mind of finishing this Linux programming interface book. But I had started a project at the end of last year that I plan on resuming working on, which is a media proxy. It's a proxy that intercepts all of your TLS traffic with social media websites and basically allows you to control what the algorithm is feeding you. Because I find one of my big problems is like my addiction to YouTube, and it'd be really nice to have a tool like that where I could just tell it like, hey, I don't want to like see any of this stuff. So yeah, that's something that I plan on picking up working on probably at the end of the month. Yeah. Are you you go on Twitch often? I've been streaming on Twitch and YouTube, and I feel like I'm getting more people show up on Twitch than YouTube. You're ultra noob. Yeah. This is some like pretty advanced stuff that I'm going through right here. I'm not gonna lie. But yeah, I mean, especially at the end of this book, like we're on page 873 now, it's starting to getting some really advanced topics, but it's stuff that's interesting. And if you're young, like you can pick it up like super fast. Like I'm old, so it takes me forever to pick this stuff up. Oh, the TLS traffic interceptor. Yeah. Yeah, I built a TLS interceptor last year, at the beginning of last year, because I had this application that I wanted to reverse engineer its network traffic with Google. It used protobufs. It was talking to Google for Firebase, I think it was. And I wanted to decrypt the traffic. And so I wrote this like TLS. Don't tell me you're a security engineer. No, I did a little bit of work in security in my career, but I wouldn't call myself a security engineer. But I do like crypto, and I do like crypto as in cryptography, and do like network stuff. So I wrote the TLS interceptor. Unfortunately, like it intercepts anything that doesn't do certificate pinning. Like if the client is pinning certificates and I can't get it to trust my man in the middle certificate that I'm feeding it, then I couldn't intercept the traffic. So I kind of gave up on that. The next step is to like dynamically instrument the mobile application that I was trying to break and like patch out like the memory that has the cert pinning stuff. But I kind of gave up on it because it's it got a little bit too hard. Want to test it on Discord? I don't really do Discord, unfortunately. I'm a boomer. I need to get better at checking my chat, like you're saying. Yeah. Yeah, I mean, I switched over to all Linux stuff at the end of last year. I was using Apple hardware and Mac stuff, like Unix, Mac OS, for over a decade, probably 2 decades. And I switched over to Linux because I just got tired of Apple, man. Like, they're just such, like, they're like tyrants, man. They don't let you do anything with your freaking computers. The way I explain it to people is like I feel like Apple and Mac OS and iOS especially, it's like they're consumer devices meant for consumption. They're not for people who actually like computers for computers, you know? And so it's like I call it Fisher Price computing. It's like you're given these like really like polished interfaces for like a consumer to consume, and there's no real way for you to understand what's going on in the system without a lot of reading of documentation. Like there's no way of like reading source code essentially because they don't really publish a lot of their source code. So yeah, I switched over to Linux because of that, and I'm running a Marchi on a couple of machines here in my lab, my home lab, and I love it. It's great. So yeah, if you are not on Linux right now, I can recommend if you're into development stuff, Omarchi is like great. This is DHH. He's the author of Rails, and he has a video here. He just steps you through everything. It takes like 2 minutes to install, and yeah, I've had like no complaints. There's a few things I don't like about it, but I mean that's with any operating system. But the great thing about Linux is that you can change any of those settings just by editing a config file. It's super open and editable. Can you share the home lab? I don't really have much upstairs here. I have a server rack downstairs in my basement. Upstairs I have a framework desktop that I got. That's what you're seeing here. That's the machine that I'm on here. And then that's piped into my streaming machine that has a Blackwell NVIDIA GPUs. I'm planning on doing some GPU programming this year, so I got that just because it's like the latest architecture for NVIDIA. So that's what's powering the stream itself. It's doing all the encoding for the stream. And then I have this crappy, oops, I knocked my camera down. I have this crappy Mac Mini. I got it because I wanted to use it as like a build machine for iOS, but it ended up, I ended up not being interested in doing that. So I think it's actually turned off right now. Yeah, it's this guy right here. So that's the third machine I have in my lab. And then I have a server downstairs. And I actually can point the camera here. You can see. So that's the CUDA build there. And that's the framework desktop. Sorry, my AV is not great. You literally have a Blackwell GPU. Yeah, it's the cheapest Blackwell GPU you could possibly get. I got it when it just was first released. It was like, I think $200, 250 maybe. I spent like a week just hitting websites and trying to like get a GPU, and I was able to get one. It was a frustrating experience to get it, but then I got it, and then I bought this book on programming NVIDIA, CUDA, like learning CUDA, and I was like starting to read it, and then I just got distracted with other stuff. So I do plan on getting back to that this year as part of the stream. What do I have running on the server? It's just file server. I like use it to synchronize my SSH and config files and stuff. Lately I've been streaming super regularly, like every day for 6 to 7 hours in 3 different sessions, because I'm trying to get through this book. And so far it's just been me and like a couple people dropping in here and there to like chat, but for the most part it's just been me like grinding through this book. But yeah, if you want to drop a follow, I'll be on pretty consistently, at least for the next like couple months. I plan on being on pretty consistently. I got a whole queue of things that I want to do, projects I want to do, and books that I want to read. I realize like reading books on stream is kind of like not something that's commonly done. And thanks for the follow. We will also hop on the yeah, cool. Yeah, I guess reading on stream is not really something that's commonly done, and it's kind of boring, to be honest. Like, I don't imagine a lot of people getting a lot out of this except for me. But it is a slight amount of accountability for me. Like, if I didn't have this accountability, I think I would just be like less motivated to get through this thing. I mean, you can see how thick it is. It's like, it's huge. So but yeah, I'm gonna check out Marchi if you haven't already. I'm gonna get back to the reading here. There is one section we have, two little tiny sections in the summary, then I'm hopping off. So I'll read those now. In short, what is it about? The title of it is The Linux Programming Interface. I'll scroll up here. There's a PDF on the internet. You can just search for it and you get the PDF. But this is basically a book that I've been meaning to read for like about a decade. I actually got the physical book from Michael Karras himself. He taught a class on containers, like a week-long training course that I took back in like back in 2019. And he handed out copies of the book for free. And so it's just been sitting on my bookshelf for like, I guess it's not a decade now. It's 7 years, 7 years. And I just been itching to read it. And I had a power outage over the holidays where my power went out, and I just like cracked it open and started reading it. And I was like, damn, like I should really read this whole thing. And it's just a survey of all of these Linux things, Linux and Unix, all these little things. Like we talked about Linux capabilities today. That was like a topic that we went over. What else? So these are the things that we're on now. So daemons, we did that. Capabilities, writing secure privileged programs, process resources. A lot of the stuff that I went over in the earlier chapters are things that I actually got in interview questions during my career. Like I interviewed for Apple one time. This is back in 2019. And they asked me about sticky bits. It's like kind of one of those like things that either you know it or you don't know it. So it's a good filter, and I didn't know it. I still got a job offer, but I felt like I was kind of bummed out that I didn't know the exact semantics of what the sticky bit is. But now, having read this chapter, I have a mental model of all the permission bits, the extended attributes, the file system inode attributes, like all of that stuff I've just like downloaded in my brain over the past week or so. And I was like, damn, I should have done this like ages ago. Because it's stuff that you just encounter constantly. And if you know it's there, it's less of a shock when you encounter it. But yeah, I don't know. I've gotten a lot of value out of this book so far. Where am I from? I'm from Colorado here. How long have I been into DevOps, IT? My entire career, basically, since like 2007, has been some amount of software engineering, infrastructure, IT, DevOps, like all the different things. I worked at maybe like a handful, maybe about 8 different companies. You started 2 years ago, man. Like your brain is just placid right now. You can like learn everything. So I encourage you to just like experiment and absorb everything that you encounter, because the world is your oyster. You can just learn so much right now and get some experience doing like real world stuff. You got your work that you do at your job. Hopefully you enjoy that, but always have side projects, stuff that you come home to and you're like, I want to get progress done on XYZ. Go to meetups. I recommend people going to meetups. I got a lot of help from mentors that I met through meetups when I was early on in my career. Because I was like an idiot when I was younger, and meeting some of these older people. I mean, you have like, obviously Twitch, you can do that as well, but going to meetups, you can get like really personal connections with people and find mentors and people that can help you along your path. And like right now, it's like a crazy time with all the AI stuff going on. So yeah, I mean, like it's exciting. It's a good time to start if you're into it. I've noticed a lot of people kind of getting bummed out about AI stuff. Yeah, AI shit. It can be totally. I use AI, like I've been using it on the stream to help me learn. Like I'll just open it up here. You can see some of the things that I search for here. I mean, I basically use it as a Google replacement. But I can like dump the entire program and everything I'm doing and be like, hey, why isn't this working? And it'll give me a reasonable idea for like why it isn't working. So it's helped me out a lot. I was working earlier on this thing. What was it? Chapter 41. So I'm doing a lot of this in 2 languages, C and Zig. And most of the book is in C. All of the book is in C. So most of my code is in C as well. So I have this like test program, and it does a forward declaration. I'll zoom in here. It does a forward declaration for foo and bar, and then it calls those functions, and then it just does a printf saying main hello world. And these functions are undefined. So basically you have to link it against something to get the definitions. So I have this library that I created that has foo and bar, and bar just does a regular printf, a call into printf, and then foo does a call into this custom printf that I wrote, which is up here. And the only thing that this thing does, it does the same thing as printf in this context, but it also writes out 2 exclamation points. So prefix the output with 2 exclamation points. And so what I wanted to do is play with how the linker and the dynamic linker dispatches the invocations of printf to see if I could get it to override stuff. So if you do build.sh here and then do run, you can see like the normal running of the program, only that foo function that is explicitly calling my custom printf gets the prefix. But if I use this LD preload thing, I can get everything. So the main will call my custom printf. I can get the library to call the custom printf. So all the symbols resolve to my library. So Yeah. There's just a lot like the AI kind of helped me out with that, figuring out like how to resolve the symbols and everything. So I have a question. As I'm from Pakistan, there aren't much tech companies here, we have, uh, but only we have here is just web applications and nothing much. So if I want to get really good with Linux as I get to do my CTF labs, what do you suggest? Um, well, I guess it depends on what hardware you have and what your goals are. I mean, web development is like web application development is like how I got started in my career because it's just so ubiquitous. Like, just pretty much every company has some form of like web app development that they're doing. So, I mean, just developing those skills. I guess you're asking like what type of technologies would I invest in if I was doing web app development. My goal is not the web development, but to learn Linux, so I'm good in terms of security. Yeah, so with Linux, I guess it depends on what hardware you have available, but Linux runs on pretty much everything. But yeah, if you can get a decent like bit of hardware, I would run Umarchi. Our Arch Linux is like a distro that they call it a rolling release. So that means that basically it's upgraded really often with the latest and greatest stuff. So you don't have to wait really that long to get the new stuff. So Arch Linux has that advantage. And Omarchi is a really nice packaging of it. So it's like really user friendly. So I'd recommend that. It runs Wayland and Hyperland, which are like newer technologies for doing like windowing. Like we have like, spaces up here. You can like move this stuff around. You can create terminals. You can launch browser. You can do like all this stuff just really quickly from the keyboard. So I'd recommend Umarchi Linux if you're looking for a distro. You can download it. I think it's a pretty beefy ISO. It's like maybe like a gig or two, but the problem with like Linux and operation stuff is that like in my experience, like there's less. I guess it depends on what you're doing. I've installed the Linux as daily use for security testing, but all I do is use already built tools. But how do I start if one wants to get totally into core and geek like Linux security and everything? Okay, you might already know of these, but I'm just gonna like spit out some names here. So Low Level Learning, he's like a guy that I really like following for that type of stuff. Low Level Learning. Again, I'm not super into security, so like I know of the topics that he covers, and it definitely interests me, but I'm not an expert in these things. He has his website Low Level Academy, if you want to do like paid courses and stuff. But he has a lot of content just on his YouTube alone. Like he produces a lot of content, like pretty much every couple days he's out with something new. And then I guess personally, I would, if you're not already doing this, look at hacking conferences. So things like Hope is the hacking conference that I grew up on. So if you search for Hope Conference, they have all of these talks posted on their website, and they have a YouTube page as well, I believe. But that's kind of how I got my kind of feet wet with some security stuff when I was younger, was a website called H2K2. I think it's h2k2.net. Yeah, this one here. But it's all the Hope Hackers on Planet Earth. They're based out of New York. The 2600 group produces this conference. There's also DEF CON. If you just Google DEF CON conference here, they have like a crap load of like content and talks. There's Black Hat. That's another one. There's Darknet Diaries. There's like so much stuff out there for hacking and like security, reverse engineering. So yeah, I mean, a lot of these are like media level stuff, but like there's also a lot of resources that they link to. So I would definitely check some of them out if you haven't already. I don't actually have a Discord set up yet. I don't think. Let me, if you hop on one of my other streams, I'll go and I'll create one tomorrow morning before I hop on, and I'll post it as a thing on my Twitch description. Actually, I'm not gonna write on that. Actually, I'll do it as a little reminder here. I'll just say create Discord before stream tomorrow. Cool. I'll close out of these. Desktop to do MD. All right, I'll just keep this down here as a little reminder for me. Yeah, I mean, my time is exactly 12 hours offset from you. It's 8:04 p.m. here for me. You can see it's at the top of my screen here. I don't know if you can see that. The other thing that I kind of am wondering about is if I need to zoom in more, or if like people can see the screen well. But yeah, I want to get this stuff done before the end of the evening, so I'm going to just blast through the remainder of this chapter here. So preloading shared libraries. For testing purposes, it can sometimes be useful to selectively override functions and other symbols. So preloading, you're interested in security stuff, like preloading libraries using LD preload is something that a lot of people use to exploit programs, because it allows you to tell the dynamic linker, hey, inject this library that I wrote that I have control over into the program, and all the references to symbols, like use that thing instead of the other libraries that you're supposed to use. So I know a lot of exploits have happened because of LD preload. But yeah, for testing purposes, it can be useful to selectively override functions and other symbols that would normally be found in a dynamic linker using rules described in section 41.1.1. To do this, we can define the environment variable LD preload as a string consisting of space-separated or colon-separated names of shared libraries that should be loaded before any other shared libraries. Since these libraries are loaded first, any function they define will automatically be used if required by the executable, thus overriding any other functions of the same name that the dynamic linker would otherwise have searched for. So again, you can get in there and like monkey with stuff. Like I was overriding printf, but you can override like malloc and free and do whatever you want. Suppose that we have a program that calls functions x1 and x2 defined in our own libdemo library. When we run this program, we can see the following output: program called m1 x1 and mod2 x2. In this example, we assume that the shared library is one of the standard directories, and thus we don't need to use the LD library path environment variable. We could selectively override the function x1 by creating another shared library, libalt. So this would be the thing that the malicious payload, which contains a different definition of x1. Preloading this library when running the program would result in the following. Yep. And you can set these as an environment variable using export, so it's not as obvious when you're running it. Here we see the version of x1 defined in libaltso is invoked, but the call to x2, for which no definition is provided in libalt, results in invocation of x2 function defined in libdemo.so. The LD preload variable controls preloading on a per process basis. Alternatively, the file etc ld so preload, okay, that's one that I haven't ran into, cat etc ld so preload. Yeah, it's not even available. Etsy conf. This is the thing that I ran into before. So I don't even have that preload configuration file, which lists libraries separated by white space can be used to perform the same task on the system-wide basis. For security reasons, set user ID and set group ID programs ignore LD preload. So that is important. So you can exploit a program, but not one that has set group ID or set user ID, but maybe one that has capabilities. Monitoring the dynamic linker with LD debug. Sometimes it is useful to monitor the operations of the dynamic linker in order to know, for example, where it's searching for libraries. We can use LD debug environment variable to do this. By setting this variable to one or more of a set of standard keywords, we can obtain various kinds of tracing information from the dynamic linker. If we assign the value help to LD debug, the dynamic linker displays help information about the LD debug, and the specified command is not executed. Cool. So I just say LD debug is equal to help cat. I wonder if I can just do a colon here and if that works. No, it has to be an actual program. Libs, relooks, files, symbols, binding. Oh, things are symbols. Oh, this is so cool. Symbols, date. Oh, so I have to say symbols like this, yeah. So this is everything the dynamic linker is doing. That's a lot of stuff just for the symbols that's looking up. This VDSO stuff, I actually have a video that I want to record on that soon. I might actually add this to my my video script. Let's do, actually, yeah. What is this? Experiments? I think I put it under there, yeah. VDSO. And this is README. I'm just going to put down here demo the use of VDSO in something like this. Cool. All right. There's all previous options combined. You can do stats, statistics. Which keyboard is that so creamy sound? It is the, I forget the name of it. Maybe it's printed on here somewhere. The Keychron. I really like it. I got it last year, and I had sworn that every mechanical keyboard is fine. They're all the same, but this one just hits different. It is the 75%. This one, not wireless. Oh, that's weird. Keyboards. I think it was this one. Yeah. But it wasn't the wireless version, or was it? Maybe it is the wireless version, but I run it wired because wireless input devices are annoying. But yeah, this is the one here. And it is super, super creamy. If you just search for Keychron, you can get it. Is it Keychron Q1 Pro? It is Keychron K2HE wireless magnetic switch keyboard. That's the full one. Yeah, it's this one here. And it was a special edition too. This one here is special edition because they got the standard version that has like RGB, but I don't like RGB. I just want the special edition white. That's what people say is like magnetic is good for gaming because you can like control the trigger point or the articulation point. I forget which one, but I don't really do a lot of gaming, so I don't really know. Yeah, the key crones are. I mean, I'm sold, man. These things are awesome. High polling rate. Yeah, I think the one I got wasn't super great for gaming, but I don't know. I don't really do. I didn't buy it for gaming. I do have a YouTube channel. Let me pop over here and I'll give you the link here. I need to like link all my stuff together. Like I just got started with this stream, so I'm not like super. Yeah, I don't have a macro in my or a what do they call it, a bot running in my channel yet. Yeah, and by YouTube I have recorded pretty much every stream that I've done so far, except for maybe like a couple. So you can tell like I just started. But yeah, drop a sub on my YouTube because I have 0 subs on my YouTube. I'm pretty sure. Yeah, I'd appreciate that. And I think I'm gonna. You're giving me some ideas here. So I think tomorrow morning before stream, I'm also going to link all my stuff in the descriptions. YouTube, and then like keyboard, framework, or let's say home lab stuff. I'll just like dump it all into the, because I've seen people on Twitch do that, where they like document like their computer setup and everything. So I should probably do that myself. Okay, so basically we got this help thing that can dump out all this information, and I really feel like diving into this more, but I gotta hop off here in a little bit. So to direct the debugging output into a file instead of a standard output, a file name can be specified. LD debug output environment variable. Okay. The following example shows an abridged version of the output provided when we request tracing of information about library searches. Cool. The value 10687 displayed at the start of each line is the process ID of the process being traced. This is useful if you're monitoring several processes, the parent or the child, but default LD debug output is written to standard error. But we can direct it elsewhere by assigning a path name. If desired, we can assign multiple options to LD debug by separating them with commas. The output of the symbols option with traces symbols is particularly voluminous. LD debug is effective both for libraries implicitly loaded by the dynamic linker and for libraries dynamically loading by DLOpen. For security reasons, LD debug is ignored on set user ID and set group ID programs. So summary. The dynamic linker provides the DLOpen API, which allows programs to explicitly load additional shared libraries at runtime. This allows programs to implement plugin functionality. That's what I've used it for in the past. Go actually has this thing called Go plugins that uses DLOpen. I don't know if you can pull a source code off of here, but let's just check it out here. Yeah. So this plugin thing, it imports C, and then where does it do its DLOpen? DLOpen. Yeah, up here. So it has a plugin lookup that uses DLSim, and it has a plugin open that uses DLOpen. And then it imports the DLFCN.h right here. So Go's plugin system is all built around this DLOpen API. An important aspect of shared library design is controlling symbol visibility so that the library exports only those symbols, functions, and variables that should actually be used in programs linked against the library. We looked at a range of techniques that can be used to control symbol visibility. Among these techniques was the use of version scripts, which provide fine-grained control of symbol visibility. We also showed how version scripts can be used to implement a scheme that allows a single shared library to export multiple definitions of a symbol for use by different applications linked against the library. Each application uses the definition that was current when the application was statically linked against the library. This technique provides an alternative to the traditional library versioning approach of using major minor version numbers in the shared library real name. Defining initialization and finalization functions within a shared library allows us to automatically execute code when the library is loaded and unloaded. The LD preload environment variable allows us to preload shared libraries using this mechanism. We can selectively override functions and other symbols that the dynamic linker would normally find in other shared libraries. We can assign various values to the LD debug environment variable in order to monitor the operation of the dynamic linker. Blah, blah, blah. All right. That is chapter 42. Ugh. Let's see here. Yeah, exclamation point book. I might add that. That'd be cool. I do have a domain I registered, but I don't have a website yet. That is something I need to work on as well. So yeah, I'll be getting around to that eventually. I do have a website, and that media proxy that I mentioned earlier, when I resume work on that, I'm actually going to be opening that up on the internet, and so like people can test it. So that'll be hosted on that domain. My Git, that's another one. My Git, I need to add that here. Git, etc. So my GitHub is cypher0-dev, and it's a new GitHub, but I'll paste it in the chat here. Let's see, github.com cypher, what is it? Cypher0-dev. I went with the name Cypher0 because I was reading this math textbook, and I learned, it's like an ancient math textbook, and I learned that cipher is another word for zero. And so the name is like 00. And there's also this thing called the Cypher0 vulnerability that I mitigated early on in my career. It's with IPMI and BMCs. Cypher0 vulnerability. Cypher0 is with IPMI. So that's the history of it. Basically, like, you could go up to any IPMI BMC and be like, I specify Cypher0 as my authentication mechanism, and Cypher0 meant that there was no authentication, and so you were just allowed access to the BMC for all these servers. It was a crazy vulnerability, and I was working at this data center at the time, and we scrambled to patch all the machines and prevent people from exploiting it. So that was something that I worked on very early in my career. So yeah, that's where the name comes from. I don't have a LinkedIn. I've never had a LinkedIn in my entire career, and I really despise LinkedIn. So, I understand some people feel like they need it for work, but I personally have never needed it, and I just feel like it's a place that people go to waste time. So I'd rather do other things that are fun than waste time on that website. That's the type of Linux I want to get into, so core, so I can create new exploit. Yeah, man, exploit development, especially. I mean, yeah. I would say it's not my profession, and it's not my specialty, but it is something that's super interested in. I think some of the work these cybersecurity professionals do is just amazing to me. Yeah, man, I feel you. Awesome, I appreciate it. All right, well, it's getting late here. It's 8:30ish, 8:22, so I'm gonna hop off. But yeah, man, it sounds like we're about 12 hours apart, but hopefully I catch you again on on future streams. And if not, like, I'm on YouTube, so you can catch me if you want to watch my YouTube streams on there. When's the next stream? Will be tomorrow morning. Yeah. I don't have email. But yeah. All right. Cool. I'll see you later.